Hello again. I'm Dr. Bettina Heinz, ready to teach you some more chemistry. And today we will look into the language of chemistry. This is extremely important to make chemistry an exact science. Before, we relied on alchemistic symbols and other symbols that were used for different cultures in the world. So we have here today Symbols and Formulas, Part 1. So these are the topics we will discuss today. The history of chemical symbols, especially in Western science. Intro to the periodic table, which is our foundation of all the elements. The elements with their names and symbols, distinguishing into metals, nonmetals, and metalloids. So the elements fall into either of these three categories, most of them, however, being metals. And then atomic and molecular elements, meaning that some elements are existing in atomic form, some are existing in paired off forms like diatomic molecules, or sometimes they arrange themselves into larger segments like phosphorus that has 4 atoms sometimes linking up to a molecular type, or 6 sulfur atoms making a nice little ring for the element sulfur. So there are polyatomic molecules as well. Here we have our periodic table that many of you already are familiar with. And I'm going to try to put it here on the Elmo so that you can follow what I will be talking about. We have here the so-called short version of the periodic table. Actually, it should be spread out. That means the rare earth group should be fitted right in between this little segment here after the elements lanthanium and actinium. The lanthanides, and the actinides. Now let's look at the table quickly. Again, we won't spend too much time on this today because we are basically talking about the elements and their names, their symbols, so to speak. And then the resulting formulas for the compounds that they make. So here we have the main series or main group elements, group 1, group 2, group 3, group 4, group 5, group 6, group 7, and group 8, which are the so-called noble gases. Group 7 is the group named halogens. Group 1 are the alkaline metals, and group 2 are the earth alkaline metals. The other main group elements also had their specific names, but it's not so common anymore. Then we have the so-called transition metals and the inner transition metals. And this little borderline here, this staircase going right through the right part of the periodic table, is the demarcation area, so to speak, about which the metalloids are organizing themselves, because everything on the left of this line are the metals, and all the elements on the right side, upper right side of this borderline are the nonmetals. So we have some wishy-washy elements sort of surrounding this borderline that can have characteristics of metals as well as nonmetals, depending on what type of partners they're dealing with. So these rare earths are also all metals, and many of these elements later on, that means with higher mass numbers, are artificial elements. They are man or woman-made elements. One interesting element here is technetium, number 43. As the name says, technetium means that it was already artificially produced. This is an interesting little instability zone here in the periodic table. And we deal with double magic numbers of protons and neutrons, and technetium has neither a magic neutron number nor a magic proton number, so it's a very unstable metal. However, it's very useful in medicine for PET scans. But we're not talking medicine today. We have to get on with our symbolism. Here I have compiled for you some interesting alchemistic symbols. Chemistry has been carried out all over the world, in China, in the Americas, in Africa, in India, in Europe, everywhere. However, every culture used different symbols. Now, our chemistry today is based more on the Western concept of chemistry that had been influenced by the old Arabic knowledge in this field. And the Arabs might have had it from ancient India. So we are dealing with essentially European chemistry when we talk about alchemy. Although alchemy is an Arabic word, alchemia. So a lot of cultural merging took place so that we have these symbols that are the originators practically of today's chemistry, the alchemists. Fire would be a triangle, air would be a triangle with a line, and so on and so on. So if we look through these symbols, you see that chemists already try to develop a language for the elements surrounding us and the compounds, and also mixtures sometimes had their own symbols, and even certain chemical transactions. Because for the alchemist, not only was the substance important, but also the procedure was just as important. So alchemists knew a lot about chemistry. Much of it is forgotten. They looked at chemistry more from a philosophical viewpoint. And they not only were involved in trying to make gold or finding the fountain of youth, but also in a philosophical sense of purification of matter. Here we have another set of symbols. For instance, vitriol, those are the sulfates. Niter stands for nitrogen. And even Dalton later on borrowed this symbol for nitrogen. Alum, tartar, fixed alkali, that means it's a certain type of modification. Potash, vinegar, wine, which of course we know is a mixture, not a pure chemical. Even urine had its own little symbol. Essential oils that you get from plants. Fixed oils, sulfur, phosphorus, phlogiston. Phlogiston was a very important fixture of the chemists before Lavoisier, and there was a big debate going on, does phlogiston exist or not? Then it was, of course, thrown out of the scientific body of knowledge, but it actually implies where you have phlogiston, you have an absence of oxygen, and where you don't have phlogiston, you have oxygen. So it's almost like a negative concept, which could lead to the same thing. Soap, glass, and look at this as a symbol of the death's head, the caput mortuum. This means an hour, like an hourglass. So when the scientists talked about a certain procedure, like boil an hour, then they would use this symbol. Or a day, a night. This is a procedure to distill, to precipitate, and this is a symbol of a very important part of the ancient alchemistic kitchen, the retort, which was still used for distillation at the turn of the century and in some modern laboratories. We see in the PowerPoint slide here an old kitchen that is called an alchemistic laboratory. So they use all kinds of things. It's a very romantic conception of the work surroundings of the alchemists. Just like a modern laboratory looks also in its own way romantic. We see here on our PowerPoint slide another representation of various symbols. So I'm just going to go through these. Here people already try to get chemicals organized in a table according to their affinities. Like associates with like oil with oil and water with water, polar with polar, nonpolar with nonpolar. So it's a table of affinities of like associates with like. In chemistry, we have two concepts, the affinity principle and the other opposites attract, like opposite poles attract. Revolutionary in the development of chemical symbols was Dalton. He tried to start organizing chemical symbols, and he relied a lot on the older concept of circular type of symbols. And these circles could be modified with a little dot, with a line. They could be colored through or left open or with bars across. Sometimes even with a letter like L, meaning lead, or copper with a C. Not only were elements depicted, but also molecules or compounds. Water used, interestingly enough, already the symbol for oxygen and hydrogen. But Dalton didn't go so far in depicting water as being H2O. So it's just HO in this concept. Ammonia also is missing two other hydrogens. Olefiant gas is a hydrocarbon, for instance. Carbonic oxide, that would be carbon monoxide in our sense. Carbonic acid was considered to be carbon dioxide. Sulfuric acid. And we see here also a very complex formula, symbol for a complex compound, which on the right of this slide is represented as potassium aluminum sulfate dodecahydrate, which is potassium alum. We also have chromium alums. We have a whole variety of these so-called double salts. We see here Dalton again. His image is represented with some old-fashioned glasses, of course. But you see here in the potash alum representation that maybe the formula is not really compact enough. The modern way is much more usable, especially in the printing context, than this outlandish figure here. But a chemist sees here already encrypted a structural formula of a complex compound. So Dalton was revolutionary in trying to organize notation in chemistry. Here is the cover of his manuscript, of one of his manuscripts. It's the original cover. And notice that they didn't call themselves chemists, yet they looked at themselves as natural philosophers. And that's why we have the talk here of chemical philosophy. This was published in Manchester, England in 1808. And important years for the change in chemical notation was in the early 19th century. That's where practically our modern notation was born. Here we have again his set of symbols. On the left, we have his symbols, and on the right, we have the explanation of these symbols. So the elements as well as compounds and mixtures sometimes involved. And here we see another page of this manuscript, and we can see already how close Dalton comes to the molecular theory. You know, he introduced the first scientifically usable atomic theory after the Greeks, which is almost 2,000 years, you could say. So we have here carbon dioxide. We have nitrous gas, which is here nitric oxide. And hydrogen gas wasn't depicted as a diatomic molecule yet. But in these lower pictures, we can see with the lines that this implies already chemical bonding lines or chemical attractive forces. Whether they are polar or nonpolar in nature has to be deducted from the contents of the book. And I must say, I haven't read this book, but it's very important to know about the history of science. So here again we have hydrogen, NO, nitric oxide, or mononitrogen monoxide, and carbon dioxide. Here we have some more symbols. This is all in French. The French were very instrumental in the development of modern day chemistry. You know, Lavoisier is considered the father of chemistry. You could almost say his wife was the mother because she helped a lot in the laboratory. And here we have already a scientific diagram of a flow chart, you could almost say a chemical reaction scheme using the older nomenclature or symbolism. Now this is an interesting diagram here. We see that Gaudin was a French chemist that believed in Avogadro's theory from day one, so to speak. Remember, Avogadro said equal volumes of gases contain equal number of particles. And this is what Gaudin showed in this view graph, and he uses Dalton's symbols. Not many people know of Gaudin, and it's not that much out there, but he did publish some important papers. Now, our modern way of symbolizing the elements and the compounds that derive from these elements is Berzelius, Jöns Jacob Berzelius, in 1813 published his ideas about improving on the symbolic ways of depicting elements. He suggested taking their names and using the first letter as a capital, and if there is some kind of contest between two elements vying for the same first letter, then you use a second letter. For instance, plutonium, phosphorus, etc. So one has P and one has Pu. But he still used some funny little signs. For instance, he crossed the line out through an element or put some little dots on top, like an umlaut or something. So it's not quite where we are today, but that was the first step. And he also suggested take the Latin or Greek roots of the original names. Here we see chemical equations already looking more like we are used to today. And here we have a little scheme of some old and some new symbols and formulas. We see a modern day organic structural formula in a modern catalog. And here we see again Dalton's potash, alum formula and his elementary ideas. So it is a long way to go from Dalton's symbol to a modern day symbol. So here this would be sulfur, a circle with a cross, and then today we use the letter S. Because sulfur is a more abundant element, that's why it's allowed to have one letter. Whereas others, like antimony, has the letters SB, coming from stibium. So this is important. The first letter is always capitalized. And if there is a second letter, it has to be small. Because otherwise, think of cobalt is C, capital C and small o. And if you would say capital C and capital O, you're not talking about cobalt anymore. You're talking about carbon monoxide. And that's dangerous. Although cobalt apparently is also not that harmless because the name comes from the cobalt, or cobalt in German, means a little evil, mischievous gnome or goblin. Now, the older elements derived from Greek, Latin, Arabic, Persian, or Old Germanic roots. K, for instance, means kalium or potassium. Potassium is derived from potash or Potasche in German. So the symbol is kalium. Although here in the English world we say, or English-speaking world we say potassium, in the German-speaking world they still use kalium as a name. So it's sort of switched. Sodium is natrium or natrium, but our name is sodium, coming from soda. Caustic soda is an old name. Cuprum comes from, or Cu, the elementary symbol copper, comes from cuprum. Aurum, Au, means gold. Hg is an interesting symbol. It stands for mercury, but it comes from the Greek hydrargyrum, which means quicksilver, translated. Here we have cobalt, and it comes from the cobalt because the mining people were very cautious about these evil gnomes that could spoil everything for them. So they were very, very superstitious in those days. Plumbum is lead in Latin, and the symbol comes from the name accordingly, capital P and small b. Tin comes from stannum, and iron comes from ferrum. Now the Latin languages, Spanish, Italian, Portuguese, French, they still use the word ferro for iron, like ferrocarrile means the iron railroad. So these are the names that come from the Old Greek or the other languages, Latin, Germanic. Later, some of the more recently discovered names came from the people who coined them, like hydrogen means water forming. Hydrogen, hydros means water. So hydrogen is part of water, so we can say water forming element. Oxygen is air forming, or it's part of our air. Nitrogen has to deal with niter, but in other languages, like in French, it's more azote, like azo compounds in organic chemistry deal with chemicals that have nitrogen, or a certain nitrogen-containing group, usually the nitrogen double-bonded segment. Radium means radiating, so it's a radioactive element. So this list is, of course, not complete, but I just want to give you some ideas how names originated. Then we have a lot of names in the periodic table that relate to a region, a country, a river, or a district even, or a city. For instance, Americium. There's also Californium that I forgot to put up here. But we have a Berkelium coming from Berkeley, Francium from France, Germanium, Rhenium, the Rhine River, Polonium, Poland, Scandium, Scandinavia, Ruthenium. Yeah, one would think it would be Ruth, but Ruthenia is a certain district in Russia, or it means Russian, sorry. Fermium, so we also have names that honor a certain scientist, like Fermium is in honor of Fermi. Einsteinium, I don't have to explain that one. Laurentium, Lawrence. Curium, Madame Curie and her husband. Darmstadium or Darmstadium, after a town in Germany. Seaborgium, a very famous scientist. Mendelevium, Mendeleev, remember the important scientist of Russia that was instrumental in developing the periodic table. Nobelium in honor of Nobel, that everybody knows is incorporated in the Nobel Prize, and his money is still available for these prizes, but he invented dynamite. Here we have names according to properties, like chlorine comes from the Greek chloros, meaning green, rubidium, ruby red, phosphorus, meaning light producer, bringer of light, radon also has to do with radiation. And we're coming to a close soon. And I'll show you some more elements. We already have seen hydrogen, oxygen, nitrogen, radon. And we're coming to our last view graph or slide. And some elements, of course, have specific meanings. Many are named after a planet, maybe, or a mythological entity, a Greek god, or a Scandinavian, Germanic type of god, a heavenly body, etc. So let's name some of them. Titanium comes from the Titan. Technetium, I already mentioned, means technical or artificial. Thorium comes from the Nordic god of war, Thor, a god similar to Mars. Uranium from Uranus. Ytterbium, xenon. Plutonium from Pluto. Neptunium from Neptune. And I also have a wonderful element that is named after the moon, but it's the Latin name, it's selenium. I think we've covered most of our elements. There are many more to go. They all have their own interesting history. So you see we have a very good grid of elements with only one or two letters in their symbolic representation. And that is good enough for us. That propelled science tremendously, especially chemistry, of course. So chemistry is a huge science. Thank you and goodbye.